So today I'm going to be talking about our recent work evaluating actually on epidemiologically motivated surrogate model of a multi-model ensemble. And I'm just going to get this out there. I'm going to give quite a high level overview of this work, kind of try and give you the narrative of what we were trying to do. And so I'd really encourage you to read the paper if you want the finer details, particularly the statistical details. And you can find the preprint here. This work was done with my co-authors, Catherine Sherratt, Kos Boss, Hugo Gruson, Johannes Bracker, and Sebastian Funk. I also wrote a short introductory blog post for this work, which I think is quite interesting, which kind of tells the story about where this work came from, which I'd really encourage you to read. I think it's quite interesting. So the overview for this talk, we're going to go through who am I, then we're going to talk about what we're talking about, then we're going to launch into some details about the surrogate model that we developed, some implementation details, the results of our evaluation, and then a summary of what we think we found. So who am I? Well, this is me. I'm Dr. Sam Abbott. I work at the London School of Hygiene and Tropical Medicine and have done so since early 2020. I'm in the Epi Forecast group, which is a real-time infectious disease analysis group. My kind of recent work has been crafting this package called the Epi Nowcast package for real-time infectious disease surveillance. I've also been working on this work that I'm presenting today, as well as evaluating the use of sequences for short-term forecasting, and on methodology for nowcasting right truncated count data. In my previous life, I did a PhD at the University of Bristol on use of the BCG vaccine for tuberculosis. I also spent some time working in finance. My kind of like daily drivers are R and STAN, and my kind of like passion is to perform analysis using novel models and interesting data, and then to generalize those approaches for others into software. Yeah, I'm mostly active in the R community, but I've also been moving more recently into Julia and Turing. And if you know lots about those, please reach out. I'm terribly ignorant. My most recent reading is a book called Modeling Discrete Time to Event Data, which is absolutely fantastic. And if anyone has any interesting thoughts about statistical modeling of infectious diseases, real-time analysis of infectious diseases, and in particular estimating transmission dynamics in real time, please reach out. And my email is there. So who am I in particular for this work? So since 2020, I've been submitting short-term forecasts and reproduction estimates to SAGE SPIMO, which is like a UK advisory body. They were used by policymakers to inform the UK pandemic response. I also produced and submitted, i.e. to the US and European forecasting hubs, similar forecasting estimates for most countries. My estimates were all based on kind of open source tools that I developed, and these are now commonly used by academics and in public health departments globally for real-time surveillance of multiple diseases. And I'm currently working on the kind of next generation methodology and tools, which is at epinowcast.org, and you can have a look at that then. So that's kind of like where I'm coming from. So what are we talking about? So multi-model, multi-team ensembles have become increasingly popular due to their apparent robustness and because of their improved performance of their forecasts. That's the spiel for the forecasting hub, and the kind of quintessential forecasting hub is the US COVID-19 forecast hub, which started up in early 2020. And that sees submission weekly of between 10 and 40 models, and they're forecasting incidents, test positive incidents, hospitalization, and deaths across the US by state and also by county. So we've submitted that, as well as many other teams. And this is kind of an example of the visualization you get, showing the ensemble and then a couple of other models. And in general, the ensemble is considered the thing that policymakers should use, and is considered to have robust gold standard performance, whatever that means. Another good example of a forecasting hub is the EU forecasting hub, the European forecasting hub. We've also submitted that as well. And that has a very similar design, has a similar inspiration, and started up, I think, in January 2021. And again, there, the ensemble is the key output. The ensemble is the thing that we should be using because it's more robust, and it's also the thing that's being described as having good performance, and is what we think is good performance. However, these ensembles and the kind of projects behind them have a range of downsides. The biggest and most obvious one is a considerable organizational resource cost required to produce them. If you're talking 10 to 40 teams of people producing a model each week, plus the organization of the forecast hub itself as a huge resource requirement. So if your forecast, say if your forecast was only 5 or 10% better than something you could achieve with a simple model, that would be quite an issue, potentially. And then another big problem, in my view, is difficulty interpreting the assumptions behind a given forecast. So particularly in an ensemble, if it's got 40 models in it, we don't really understand what is driving that forecast and what it means, and therefore how can policymakers make use of it. Like, does it, for example, capture their most recent intervention? Does it capture their vaccination campaign? We really don't know. And how do we tell? And that's, I think, quite a big problem with these sort of ensemble projects. So to get around that, those issues, emulation is often used in climate modeling as a solution. And basically that's generally some sort of non-parametric simplified statistical model of a more complex mechanistic model. However, that really doesn't allow you to have any interpretability, which is something we think is really important. And particularly if we're making policy decisions on these models, we really want them to be interpretable. So can we do something similar to this kind of emulation, non-parametric statistical modeling concept, but without losing interpretability and also without making it a black box? Because as we've seen throughout COVID, it's really important that our models are easily communicated to those who use them and also to the general public, because otherwise they won't trust them, which is totally fair enough. So our kind of core tenets that we're aiming for: we want to understand our model's behavior. We want forecasts that are good in some sense, and defining good is hard, but here we'll go with what the community at large thinks, and that's encapsulated by what we see in the ensemble. And we want forecasting to be relatively cheap. We want it to be easy enough to do that you can do it, with your own computer, with quite limited resources, and so you're really democratizing access to this kind of like gold standard of forecast. And the big question for this paper and this work is, can we create a model with these features? So the key here is we're not trying to make the best possible model. We're trying to make a forecast model that looks like the ensemble. So the ensemble might have some features we don't necessarily agree with. It might have some behavior that we don't particularly like, but that's okay. What we're aiming for here is to produce a model that replicates the ensemble, and then we can understand the ensemble and also provide it as a service without trying to provide the best possible model, which is a slightly different target to most forecasting. So how did we go about doing this? So first things first, we reviewed the hub ensemble and derived a set of observed behaviors. We then review our previous forecasting hubs. As I mentioned, we've done quite a lot of work on this, and those of others to explore the kind of assumptions we commonly make in our models. And then we make a set of assumptions that we link those assumptions we've made in the past with the behavior we are seeing in the forecast ensemble. And then we define a model based on these assumptions. And then obviously we need to understand how we done a good job, how we've not done a good job, where have we slipped up. And so we evaluated this in real time for 6 months. So that's producing a forecast every week, submitting to the forecast hub, and then looking in real time, how have we done? So rather than looking back retrospectively and then potentially being barred. So the surrogate model, what is it? Firstly, what are our insights? From the forecast hub, European forecast hub, we know the ensemble is an unweighted quantile median of independent forecasts. We know the models are a range of different constructions, and those are generally mechanistic, statistical models, hybrid statistical and mechanistic models. That's where most of ours sit, and also human judgment frameworks. We see they're typically robust to daily reporting artifacts. So you might have, for example, a big spike in reported cases on one day of a week, and usually ensembles robust to that. And also, interestingly, some ability to forecast future changes in trends that were not clearly present in the observed data, which might not sound like much, but it's not generally a property of most of the forecast models that go in to the ensemble. And then also highly correlated over time, and generally less reactive during periods of stability, i.e. so it's less likely to predict a change in trend if in the last kind of couple of weeks, couple of months, it's been a very stable trend. Which again is not necessarily a good or bad feature, but it is a feature we observe in the forecast ensemble. And then I think finally, relatively sharp forecasts with perhaps a noticeable bias away from forecasts that are significantly larger than currently observed cases. So what I mean there is it's not, when you're near somewhere that looks like peak incidence, it's more likely to predict a downturn than it is an uptick in cases, which again is not necessarily good or bad behavior, but it's just the kind of emergent behavior we see. So our forecasting models, there's quite a lot of different submitted forecasts I'm not going to go into here, but these kind of observations are mainly drawn from this work with Nikos Boss, comparing human and model-based forecast of COVID-19 in Germany and Poland. So the Germany and Poland also had a forecast hub, and that's where these are drawn from. And so there, we focused on trying to minimally represent the infection process while maintaining statistical flexibility. We had a negative binomial likelihood with a log link. We used daily data with an adjustment for the day of the week effect. We adjusted for changes in susceptible population. And generally, we captured the changes in trend quite well, but we were very susceptible to outliers. We typically over-predicted during periods of growth. And if you read the paper, which I really encourage you to do, it's really interesting, the human judgment models really outperformed our attempts at forecasting, which I think is quite interesting. And yeah, read the paper, it's really cool. Nikos did some really great work here. So from these two kind of sets of observations, and in the paper there's obviously quite a lot more detail, we pull out a set of observations. And so these observations are the ensemble is robust to daily reporting artifacts. It has some ability to forecast future changes in trend. It's less reactive to apparent observed changes in trend than our own forecasting submissions. It produces sharper forecasts. It has a tendency towards underprediction, and modeling the reporting process appears to have little impact. So that's from our work, trying to model that minimally and seeing how that did or didn't do in comparison to not trying to do that. And so based on that, we pulled out some assumptions. And these are: reported cases can be modeled using weekly data and a generative process discretized by week, so rather than daily. Reported cases can be modeled as if they represent infections. So this is talking about not trying to remodel the reporting process. The growth rate of infections can be represented in an autoregressive process with an order of 1 week. Unobserved interventions and more generally changes in transmission towards a stable state can be represented using a multiplicative decay parameter. So I'm going to show the equations in a minute, which makes that a little bit more clear. But essentially, this is saying that there should be some adaptation out of the horizon of our data towards interventions being put into place or interventions being lifted. We are assuming that we can model autocorrelation by looking at just data on a weekly scale and also using this simple order 1 ARIMA process. And we are also just implying that the epidemiological structure of our data doesn't really matter, and we can just pretend that reported cases are infections. So what does this look like? These are the equations. Great. There is quite a lot more detail on this in the paper again, but essentially this is a weekly AR1 growth process on the growth rate with an additional decay to a steady state. And that's on the second from bottom line. That's the kind of core little bit of methodological flourish. So there we're saying that when you're above or below 0 for your growth rate, you have a different multiplicative decay towards 0, which is allowing for more rapid interventions when you have good growth, versus when you are in a decay period. So that's what allows us to kind of capture very simply some idea of like an MPI, right? So it's really, really basic, but that's just allowing some kind of trend towards no growth. And then everything else here is very self-explanatory. So implementation, what did we do? We submitted to the European Forecast Hub from February 2022 for 6 months. The model's all written in Stan, and it's an extension of another package that I wrote called the forecast.vox package, which came from some other work, and therefore is really modular and is really easy to adapt and hack on. It was developed using GitHub Actions, which if you've not checked out, I really encourage you to, and that really limits the amount of computational resource and also ensures reproducibility for others because it's a public compute resource that we've leveraged. And then because of that, we were unable to submit our models in an automated fashion to the GitHub Actions ECDC Hub framework, which meant no manual intervention during the submission periods. When we say this was real time, there's evidence of that because it's from something like versions that we haven't touched. And then the evaluation is fully reproducible, ensuring that the complete analysis can be replicated if you're interested, and also you can hack on it and develop similar projects, all with the same code base, which I think is quite important to make sure that these kind of results can be generalized. So what did we find? Sorry, I just had a repeat slide there. What did we find? So this shows forecasts from the surrogate model and from the ensemble model for some select number of countries, both on the natural and log scale, and also their weighted interval score. I don't really get into how we're scoring it here. It doesn't super matter. Well, it does super matter. It's very interesting, important, but it doesn't so much matter for the narrative that I'm going for here. You can read more about it in the paper. But the basic core bits to pull out from this figure, there's quite a lot going on here. In our example set of locations, the absolute performance of the ensemble and the surrogate model was like fairly visually similar on the log scale in most locations. On the natural scale, the difference in performance is much more marked, and in particular around periods of peak incidence, you see that the surrogate model was much more likely to overpredict. And we also see that just in general, performance was not homogeneous across locations, with some places like Slovakia having performance being much more similar, and in other places like the United Kingdom, performance was markedly different. We see that for both models, forecast horizon meant a decrease in performance, which makes sense, but this was probably worse for the surrogate model. And just in general, during the study period, the ensemble appeared better able to forecast peak incidence than the surrogate model, which again, you can kind of see on the natural scale being quite obvious. Both models did quite well at capturing large reductions in Poland, but we did see that the ensemble spuriously predicted some large reductions in, for example, Germany, that the surrogate model wasn't reactive to, which is a slightly odd difference that we're not totally clear where that comes from. So looking at this on a more quantitative scale, so this is using proper scoring rules and relative scoring rules. So this is relative performance to the ensemble. So we're saying, are we better or worse than the ensemble? What we see is that in general, the surrogate model was about 25% worse than the ensemble model. So just going back a step here, what we can see here is the relative weighted interval score and absolute error in the top right-hand corner. And then we have the distribution of the score, the relative weighted interval score by horizon, top left. Bottom left is by forecast month, right-hand side is by location. So that gives you the kind of like really a detailed view of the differences in performance in different places. And yes, so the ensemble was about 25% better than the surrogate model just in general. And performance of the surrogate model relative to the ensemble model degraded over time, over forecast horizon. And what you can see from the distribution plot is much of this outperformance was due to kind of quite a small subset, like a tail area of the forecasts, and the majority performance is quite a lot better. And if you just consider median relative performance, which is slightly dodgy because there's no proper scoring rule, but there we are. You see that the difference in score is quite a lot less, and that the degradation over the increase in forecast horizon is also quite a lot less. So that indicates quite heavily that the skewed score distribution is responsible for this like large difference. And in general, there's a lots to dig into here that we dig into the paper, but just in general, about 30% of surrogate forecasts scored better than comparable ensemble forecasts. About 70% were in 50% of the comparable ensemble forecasts, which is, borderline okay. That's probably acceptable given that this is something that runs in 10 seconds, the massive resource cost of the ensemble forecast. And then 17% had more than 100% worse weighted interval score than the comparable ensemble forecast. So that's obviously bad. And those are the outliers that we don't want to happen, and would mean that we'd struggle to trust this surrogate model in many circumstances. So there's lots more to unpack about forecast performance of both the ensemble and the surrogate model. And I'll leave that to those who are interested to go and read the paper. But something I just wanted to highlight was that the overall surrogate model was fairly well calibrated. And generally, when we talk about forecasting, we want our forecast model to be calibrated above all else. So we want its empirical observed prediction interval to match up with its actual interval, essentially. And we see the surrogate model does that quite well. And interestingly, the ensemble model is really quite poorly calibrated, and it's really overconfident. And that's very odd, because that's not a characteristic that we want from a forecast model, particularly one that we are saying is somehow a gold standard. And if we break down the weighted interval score by forecast interval, we see the majority of the poor performance of the surrogate model was in the tail, and the tail is the bit that the ensemble doesn't have because it's poorly calibrated. which maybe indicates a slight breakdown in how we're scoring here, which is the way that the ensemble, the hub score, and basically the whole rest of the forecasting community score for infectious diseases. So we're not doing anything different here, but it maybe indicates that the way we're thinking about doing these scoring is perhaps not as correct as it could be, and there's work to do there. And then finally, there's some bias issues. So the ensemble is relatively unbiased, but our surrogate model is really quite biased towards overprediction, which is not a good trait at all, and is not something that we really understand what part of the assumptions are driving that. So obviously I could go on and on about this, but I need to wrap this up. So I would, yeah, as I said, check out the paper. There's a lot more. But in general, I'm just going to summarize. So what were we talking about? We were talking about improving access to ensemble quality forecasts and also trying to understand how they work. What did we do? We developed an interpretable surrogate model based on our observations of the ensemble behavior and our prior forecasting experience. What was that? It was a weekly AR process on the growth rate with an additional decay to a steady state. So nothing groundbreaking. But the key here is the kind of novelty is we are trying to replicate the ensemble and we're trying to do it in an interpretable way, and then linking assumptions to the model construction. You could generate many other models from this, and it's something I'd be really interested in seeing other people's view of what the assumptions are and how they link to how the model should be developed. I'm really hoping that people take our reproducible code base and our kind of like pipeline for doing this and hack on it themselves, because I think there could be some really interesting work. As I said, yeah, implementation, it's all reproducible and there's a big focus on that, and I really hope people dig into it. Our results, some qualitative similarity, but with increased uncertainty and generally quantitatively worse performance, but as kind of discussed, actually relatively close in quite a lot of circumstances. Depending on setting and situation, that might be a big issue, or it might not. And if resource costs are a big issue, then it might be okay to have this kind of model that reproduces behaviors mostly, but not always. And then the key kind of odd thing that we picked out was the improved calibration beats the ensemble, and the fact that calibration is something we want and the ensemble doesn't have it, and that's not a good thing. And something we could try and do with this surrogate approach is try and replicate a model that is poorly calibrated, so we can understand where that poor calibration is coming from. What's left to do? How can we do this better? Should we even be trying to replicate the ensemble, or do we always want to be trying to target best performance? What does that mean if we're saying the ensemble is the gold standard? Can we get to that gold standard if we don't have an ensemble? I think there are some interesting questions. I'm really looking forward to other papers that people write about this. And yes, thanks very much for listening. Thanks very much to my co-authors who honestly, as ever, did all the work. The reviewers, this is under review at the moment, and I think hopefully it'll be out shortly in the new year. They had some nice things to say, and also they said they didn't know how to use a comma, but they're entirely correct then. And also, this couldn't exist if people didn't participate in these forecasting hubs. So thanks very much to everyone who submitted forecasts. And thanks very much to all the hub teams who compiled the forecast, which is a huge amount of work, and generated the ensemble, which again is really, really hard. But anyway, thanks very much for listening. And I really appreciate the opportunity to present this work. So thanks very much.